SwayamPrabha. Digital India. Educated India.
Hello everyone. In today's lecture, we'll be looking at the jump conditions on an interface in the presence of surface tension. Now, just to quickly recap what we've seen in the last few lectures, we first derived the jump conditions interface without surface tension, and then we looked at what are the consequences of surface tension, and we noticed that if you have surface tension at a curved interface, then there is a discontinuity in the pressure across the interface, which is referred to as the Laplace pressure jump. The idea of doing this kind of an analysis is to take an interface as shown in the figure here and consider two fluids. Either it could be A and B, or minus and plus, or it could be 1 and 2, depending on a variety of different notations are available. Okay, and we take a small control volume on this interface and ask what are the jump conditions across an interface like this, separating two fluids. Now, quickly to recap your memory, we looked at a situation like this where we looked at jump conditions on interface without surface tension, and these are just something that I'm writing down from the previous lectures. And we noticed that the tangential stress is continuous across an interface without surface tension, and in the absence of surface tension, this is the normal stress condition. And for a static fluid where there is no motion, then all the velocity terms drop out and the pressure is the same on both sides of across the interface. Okay. Now we will analyze this problem more carefully. In some sense, we are returning to this problem by now including new forces such as surface tension forces. So let's start with a small control volume. I'm showing you a control volume with minus and plus, or 1 and 2. Now I want to just focus only on the volume here, this little volume shaded region. Now there are a bunch of vectors that I have to first represent so that the convention is clear. So we'll first start with writing down the tangent vector. So there are two kinds of tangent vector. We have m hat here. This is one tangent vector which is stretching the interface. But since I've shown this in 2D, I can't show another tangent vector, but there are two tangent vectors at any given point, and they are orthogonal to each other. So I could have another tangent vector, let's say here, if this is, so we are talking about fluid A and B, or plus and minus. So I could have another tangent vector. This is a tangent vector in fluid B. And similarly, I could have a tangent vector in fluid A as well. And when we make the 3D drawing, you'll see that these two vectors have a different orientation compared to the tangent vector M. We also have a normal vector, the normal vector in fluid A, which we'll call it as NA. So small correction here, this should be A and this is B. And the normal vector in fluid A, we'll call it as, this is pointing from the interface into fluid A or B. Okay. This is NA. Additionally, we will define a normal at the interface, which we'll call it as just N. Okay. And therefore, if I were to write it down, so if I say this is NA, or I could even have N minus, and this could be N plus. So clearly N hat is N plus, which is negative of N minus. So this is the convention that I will choose, that N hat, the normal vector, is pointing from minus to plus. That's the convention that I'm going to use. Okay. The control volume has a thickness of, let's say, L. We will eventually repeat the analysis that we had done last time, where we take this control volume and shrink it to 0 thickness. Okay. Now, I can't represent both the tangent vector in this two-dimensional drawing. So we look at a three-dimensional drawing. So here's a spherical cap. So we have a curved interface. On this curved interface, I'm looking at a small region, okay, a small control volume of finite thickness. I'm not showing the control volume, but I'm showing the surface, okay. Now I have a small surface S. So S is a small surface on the interface with C being the bounding contour. So S is enclosed by this boundary C. S is basically a curved surface. So at any point on the surface, the normal vector is changing orientation. Okay. Now further, I'm showing you two tangent vectors here. One tangent vector M that I'm just highlighting in a second here. This one tangent vector M is going along the contour C, and the other tangent vector T is perpendicular to this contour C. So that's the idea. And I have N which is perpendicular to both of these tangent vectors. Now I could actually take a top view of this. The top view of this contour would look something like this, where I have at any point on the surface, I have a tangent vector outwards, that is T, and M is along this contour, and N, you should think of N basically coming out of the screen. Let's say M is this way. And clearly, as you go along the contour, which means that as you go along this contour C, the orientation of all these unit vectors change. For example, somewhere here, T would be outwards here, whereas M would be along in that direction. Okay, and N is perpendicular to the screen as you're looking down. Okay. So some useful identities. Since N hat, M hat, T hat are mutually orthogonal to each other, orthogonal set of unit vectors, we have N cross M is minus T. That's the first relation between these three unit vectors that I have. Okay. Now at any point on the surface, I have a small control volume that I have taken on the surface. I can take a small region and ask what are the forces on that region. For example, I could take a small element like this along the surface, and I could ask what is the force that is acting on this region. Now you can clearly see that this force that is acting on this region would basically be gamma T hat in all directions. So if I were to take this region here, then if I were to take this region here, it should become clear. This will be gamma T hat. That's the forces on this element. So the force basically changes depending on where you are on the surface. Now we'll start by writing down momentum equation to this control volume. This is something that we have done earlier, but now we have one additional force, which is the surface tension force gamma T. Let's quickly write that down, all the terms. This is basically the time derivative term. I have body force here. Then I have the surface force. Then I have the stress term. This is from the stress tensor. The second term on the right hand side is basically talks about the momentum flux across an interface and relative to it. Then I have the stress tensor term. This is basically the surface tension force because of stress tensor. The momentum balance flux because of stress tensor. And finally, I have a new force, which is surface tension let's quickly look at where this force is acting. This force is acting all along this contour. Okay, so if I were to take this contour C in this figure is being stretched equally in all directions. This is being stretched in all directions, not necessarily equally. I stand corrected there, because the value of surface tension need not be the same everywhere. The force that is of interest to us is gamma T. We'll later shrink this region to a very small size, and then the variations in gamma will explicitly enter this analysis. So you can clearly see that this force acts all along the contour. So it's a contour integral. So I go along the contour, and as I go along the contour, the variable that is changing along the contour is dl. So L is the variable that is changing along the contour. So as L increases, I'm traversing along the contour. Okay, so L is arc length along the contour C. Okay, gamma is surface tension. Now we know the other forces here. The rho times d fi dv. This is basically the body force. Then we have the let's write down all of them. This is the body force here. This is the hydrodynamic force, hydrodynamic surface force. Okay, and this last term here, this is basically the surface tension term. Now, like before, what we will do is we will basically take the thickness of this contour volume and shrink it to 0. Okay. We achieve this by taking the limit L goes to 0, where if you recall, L is basically the thickness of this contour volume, and therefore all the body force term volume derivatives go to 0, and I'm left with only the surface forces and the line integral. Let's write down all the terms here very quickly. So the body force is, the left hand side is 0, the body force is 0, and now I can write down this expression on both sides of the interface. Okay, because both these surfaces basically go to 0, and the curved side of the contour of the volume element does not contribute because the thickness goes to 0. So now I have the one surface at the top, which is the plus side, and another surface is the minus side. Both these surface integrals, I can write and separate them out as plus side and minus side. So I'll start with the plus side. I have plus side So you can hopefully you can see the expression as well. So I'd like you to try and write it down with me. So I have nj. I'll call this as the plus side. uj minus wj uids plus, or I can write down on the other side as well, that is minus. Each term, let's separately write them down. nj minus uj minus wj uids. That's on both sides for the hydrodynamic force, surface force term. Then we have the stress term, stress tensor term, which is plus nj sigma ij, where this is plus side. I have plus nj sigma ij on the minus side. This is ds. And finally, I have, this is a closed contour, contour C, gamma dl. Gamma T, that's the force, dl. So that's all the terms that I've written down here. Now, recall nj plus, nj minus is negative of nj plus. Okay. And therefore, wherever there's nj plus, I can simply write it as nj, and nj minus, I'll simply write it as minus nj. Okay, that's a convention that we followed earlier as well, so nothing new there. So we'll write down all these terms again. So I have this is on the plus side, rho nj uj minus wj uids. Now I have the minus sign there, so that becomes plus rho nj uj minus wj uids. The hydrodynamic force term is done. Now the stress tensor term, plus the stress tensor term, and finally I have the surface tension term. So now that we have written down all these things, okay, we can also, for those who may not be very comfortable with index notation and more comfortable with vector notation, I'll quickly, for your benefit, I'll quickly write the same thing in vector notation. There's dot there. So that's my expression in vector notation. Now, there's a useful identity. We will be using the following identity to convert the line integral into a surface integral, I won't be deriving this identity step by step as part of a regular lecture, but I will be providing necessary material where the derivation of this identity is shown. So what is the identity that I'm talking about? So this is basically the identity of surface tension dl. This essentially becomes a surface integral. I have del s gamma minus gamma n hat del s dot n ds, where del s is, you can say, is a surface gradient operator, and for a flat interface the regular gradient operator del and del s mean the same, but to distinguish that this is a surface gradient operator valid for taking the gradient of a scalar quantity along a curved surface where n hat, the normal vector, is changing orientation. We put a subscript s to show that it's a surface gradient operator. The surface gradient operator can be related to the regular gradient. If you know the regular gradient, then if you know if you know the normal vector, then you first define the tensor like this. I is an identity tensor, n is another tensor. You take a dot with the usual gradient operator and you get the surface gradient operator. Or in vector notation, I have this is del minus n del by del n. So this is my surface gradient operator. So if I were to just substitute the surface gradient operator into the expression, what do I now get is we now get on the plus side. What are the terms on the plus side? We have the hydrodynamic force, the momentum flux passing through and across an interface, and the stress tensor term. There are two terms here. And I've taken this to the left hand side. So I have sorry. This is on the plus side. And on the minus side, we have the same terms I have both of these terms, and these two terms is equal to the surface tension term that we saw, which is surface gradient of gamma minus gamma n hat del dot n. This important relationship that I have is basically the jump condition across the interface. We can take it one final step. Because this is valid for an arbitrary ds, I can, for this expression to be valid at all times, I have there's the first term, this is on the plus side, I have the same expression on the minus side. This is in the above expression, the stress tensor sigma has pressure term plus the viscous term of the deviatoric stress. What you have derived here is jump conditions or jump condition at an interface with surface tension. Clearly, this is a vector equation. What we want to now do is to analyze this in separate components, which is the normal component and the tangential component, which is exactly what we'll be doing in the next lecture. So I hope you've seen how additional surface tension brings in a new term into this jump condition. And if surface tension is exactly equal to 0, I would like you to go back and verify that this expression that we have derived here exactly matches with what we have done earlier, where we did not have surface tension.